Hello everybody and welcome back. We're going to continue on looking at the Csmc, that's the Canadian Senior paper put out by the University of Waterloo. We're specifically looking at the 2012 paper. We're on to question 3 in part B, which is in fact the last question in the whole paper. So let's take a look, and hopefully you guys have tried this question before. It's so much more engaging if you tried the question already. So, 3. So we have an A, B, and a C part. So right-angled triangle PQR has its right angle at vertex Q. PQ equals 6 and QR equals 8. So it's a 6, 8, 10 triangle. If M is the midpoint of QR and N is the midpoint of PQ, determine the lengths of the medians PM and RN. Okay. So let's get our bamboo paper out and continue on. So let's draw ourselves a little picture. So we're looking basically at, I want to draw some medians, so I'll make my right angle at the top. So that's Q, we'll say this is P and this is R. And we have M and N are midpoints. Midpoints of which ones? PQ and QR. Okay. I can't remember which one's M and N. Let's say this is M, this is N. We'll just double check that. M is the midpoint of QR and N is the midpoint of PQ. Okay, so I think I have those backwards. And we want the lengths PM and RN. Okay, so N over here and M over here. We'll give these guys a different color. Let's say orange. Okay, so they're medians. One of the things that tells us is that they split the side lengths in half. So what were these side lengths again? I think it was QR is 8, but we'll just double check that. QR is 8, PQ is 6. Okay, and we want the lengths of the medians. So this is 6. And this is 8. So medians split these things in half, these sides in half. PN is NQ, and that's going to be 1/2 of PQ. 1/2 of 6, which is 3. And likewise, RM is going to be MQ. It's going to be 1/2 of RQ. 1/2 of 8, so that's 4. So we want the orange lengths, the medians. Well, PMQ is going to be right angled. Same with RQN. And this gives us a perfect avenue to determine the length that we want, the lengths of these medians. So PM squared is going to be MQ squared, which we know, plus PQ squared, which we know. So that's what? 4 squared plus 6 squared. So that's 16 plus 36. So we can get out our calculator if we need to. But if we don't need to, we can see that it's just going to be 52. So that's the square root of 52. 52 has a factor of 4. So we can bring that out. We get 2 root 13. And the other length that we want, Rm, well, Rm squared, Rn squared. Rn squared is equal to nq squared, which we know that's just 3, plus qr squared, which we know is 8. So 3 squared plus 8 squared. And that's just going to be 9 plus 64, which is 73. Now that doesn't have a nice, we can't bring out a whole number out of that, but we do know that Rn is then square root of 73. We can box these so we know we have the right answer. We know where they are. And that gives us A part. We determined the lengths of the medians that we were asked to, PM and RN. Okay. So B part. Triangle DEF has 2 medians of equal length. Prove that triangle DEF is isosceles. Okay. So we're not told which medians they are. So we can draw a picture and make a guess, say that maybe it's the median splitting DE and EF. Who knows? So, draw ourselves a little picture on a new piece of paper, and we get something like, we'll say it's DEF. Their lengths are equal. So we'll draw M over here, and we'll draw N over here. Just as before, we'll give ourselves some orange medians. So our assumption is that these two guys are equal. Okay. So where do we go from here? Well, we want to prove that 2 of the sides are equal. And we can see pretty quickly by symmetry that we're going to be showing that DE and EF are equal. Okay? DF is the odd one out. He's the one who's not intersected by one of these equal medians. Or he's not touched by either of these equal medians. So it's pretty clear that if for some reason we had this set up and DEDF was equal, then there's no reason we couldn't flip the triangle and say EFDF is equal, in which case then we'd be forced to have an equilateral triangle. And that might be the case, but that's highly unlikely. We're just asked for isosceles. If they wanted equilateral, they'd ask us for equilateral. So we're going to try and show that DE and EF are equal. Okay, so how might we go about doing that? Well, one thing we know is that since these guys are medians, they split their sides equally. So now if we could show that EN and ME are equal, then we'd have the sides are equal. Okay. Now usually when I see a triangle set up like this and I have the side lengths in half, split in half, I usually like to draw this middle line MN. Gives me a smaller triangle that happens to be congruent to the bigger triangle. And I'll show you why in just a moment. So triangle MEN is 1/2 of triangle, well, it's 1/4 technically. Of DEF. How do I want to write that? So it's congruent to the triangle that is similar to triangle DEF. Alright, if we take a look at MEN, these two side lengths are 1/2 of the side lengths of DEF, right? But this angle in here, well, it's the same for both. So by side angle side congruency, we see that MEN is really just the midpoint of the halfway triangle of DEF. And from there it follows that MN is equal to 1/2 DF. And in total, MEN has 1/4 of the area of DEF. Okay? You get a similar triangle when you connect up the midpoints on two of the sides. So MEN is similar to DEF. It's 1/4 of the area or 1/2 of it in terms of side lengths. Either way you want to think about it is fine. Okay. Now MN is 1/2 of DF. Right? This is 1/2 of this. And it's also parallel to DF. Why? Well, this guy in here, this smaller triangle, we can say that that's alpha, that angle is beta, and this angle here is gamma. By similarity, this has to be beta and this has to be gamma. And that means that we're going to have parallel lines here. Okay? Both MN and DF strike EF at the same angle. They're parallel. They both strike at an angle of gamma. Parallel, not parallel. Right? Written style question. We are in part B, so we should explain ourselves. By similarity to DEF, both M and N, both line MN and DF will have to hit the line segment EF at they both hit the angle hit at an angle of gamma, and that means that they're parallel. They both hit at the same angle to a given common line, and these lengths are parallel. Okay. So since M and N are parallel, we can make some other observations. This angle in here, which we'll call dot, same as this angle here. So since MN is parallel, to DF, so we have angle NMF is equal to angle DFM. And this one in here that we'll call X, by the exact same reasoning, we have MND is going to be the exact same angle as FDN. But notice also we have these two lines intersecting each other, so the angles that are opposite each other are also going to be equal. So what's that? Let's call this point of intersection P. P for point of intersection. So DPF is going to be the same as DPF will be the same as NPM. So that's the intersection of FM and DM. So that means that PMN and PFD are similar triangles. So MNP and FDP so these guys are similar. Not only that, we can tell the ratio of their sides. Because we already know that MN is 1/2 DF. So we can easily conclude that MP is going to be 1/2 of, which one is it? Basically, we take this triangle, we shrink it, and we turn it around, so MP is going to be 1/2 of PF. And the other one, NP, is going to be 1/2 of PD. But we know that 3ND Right, so that if ND is a half PD, then PD is twice ND. Sorry, NP. Getting ahead of myself. Not ND, NP. NP. So 3 times NP is going to be ND. And that's one of the medians. And we know that that's equal to MF, which is going to be 3 times MP. So from there, it follows that NP is equal to MP. So what have we just shown? We've shown that this smaller triangle here is isosceles. Okay. Now it'd be nice if he happened to be congruent to this triangle right here, not congruent, similar. And that would mean he's similar to DEF, and we want to show DEF as isosceles. But as it stands, all we know is that MP equals PN, so MPN is an isosceles triangle. But it's similar to DPF, so that's got to be isosceles. And then from there, I think we can get DM equals NF. So by similarity, our other two, PD is equal to PF, right? Because DPF was congruent to NPM. So if I'm going to work this out, I need to take a look at my picture again. That's that, and that. So MPD is equal to NPF. Right, these are still just opposite angles in a line intersection. So by side angle side congruency, triangle MPD is congruent to triangle NPF. And it follows from there that DM is equal to Fn as lengths. And so finally DE, which is twice DM, because the median splits the length DE in half, which is then twice Fn, which is equal to EF. Oops, E only has 3 lines. So DEF is isosceles, which is exactly what we wanted to show. Okay. So it all comes from our instincts with medians. Once we see those two midpoints, we have them isolated. The instinct is to draw in MN. And we get a quarter of the area and a half of all the side lengths, and basically a similar triangle there. And from there, it was just a bunch of angle chasing. Once we knew MN was parallel to DF, we got that angle was equal to that was equal to that, these angles here and here. And we were able to sort of chase it around and get equations that used the equality of our two median lines to show that we had smaller isosceles triangles, and from there we got more congruent triangles, and the result followed. Okay. I think that was B part, so we still have a C left to go. Alright. Triangle ABC has its vertices on a circle of radius R. Okay, so that's going to be the circumcircle. If the lengths of two of the medians of ABC are equal to R, determine the side lengths of triangle A, B, and C. Okay. So what are we going to do here? Well, it's probably best to start off by drawing a picture. So we get ourselves just a brand new piece of paper, because I don't want a picture down here and then have to keep referring back to it. So let's try and make a big picture. So we have A, B, C, and we have a circle encompassing these. You know what? I'm going to draw my circle first. I think that's smarter. It's harder to fit a circle to 3 points than to fit 3 points on a circle. Now, we're given that it's a radius of R, so I'm going to include the center right off the bat. Oh, this makes me wish bamboo paper had a compass function. It probably does somehow, maybe. So we'll include our center. We'll call him O. I'll make it kind of small so we don't get in the way of any of the lines we're drawing. Now, I don't quite know where A, B, C will lie relative to O. I do know, however, that AC, AB, and BC all would be, they have a bisector, a perpendicular bisector of their angle when it comes to drawing the radius in between them. So that might be helpful. But I don't know. AC might stretch all the way down here. I really don't know how it's going to look. So take your pictures with a grain of salt. I wanted to, I could probably, AC can lie above O, it can lie intersecting O, giving us a diameter, or it could lie below. You're welcome to draw 3 different pictures for it. But as I just want some intuition, I'm not going to draw anything yet. Now we're given that A, B, and C have 2 medians of equal length, I believe. So radius R, 2 medians are equal to R. Okay. That's actually kind of interesting. So 2 medians both equal to R. So what can I do? Well, I can sort of, no matter what, I can drop a radius of R here. And let's use our trusty orange and draw in some medians. Okay, and should start with the side I'm having first. No, this median's getting redrawn. First one was oh so nice, but the second one was a no. Okay, so we have our 2 medians. We should probably give them names. M and N sound good again. See, in the last one I put M on, I did it first, and then I remember in the first example they had an M opposite the smaller, the lower letter. I don't know, I'll go with my instincts, which is our M and N here. Okay. And we know that these guys are O. So OC OA, OB. I don't have OA and OB drawn in here, but this is just for my records. So these are all equal to R. And again, I don't quite know if, it might turn out that AC is a diameter or something, which would make this question probably a little easier. Now, by our work in part B, we know that ABC is isosceles. And so the way we have it drawn here, AB is equal to BC. Okay. Okay. Well, I know that if I draw a radius that bisects the line segment AC, if I split that in half, it'll meet it perpendicular. So let's draw in another color. And I'm drawing this in a very special way, and actually I'm kind of mad with my lines, so I'm going to have to redraw it and redraw the orange lines. But what I'm noticing is that OB is actually going to be the line that bisects these guys perpendicularly. What's with me today? I can't seem to draw a straight line for the life of me. Oh, there we go. Much better. Alright, we'll touch up our little orange lines. In fact, if this gets any more complicated, I may have to just redraw this altogether. So I'm going to draw this in, and then I'm going to explain it by writing it down. But I know that a point, there lies a point somewhere on the circle that splits the chord, so that O to that point splits the chord AC in half. These are medians, so that should be added in. But I also know that B to AC also splits it in half, so this point has to be the same. We'll call it P for intersection. So we know that it splits the chord in half, so AP is PC. So by isosceles-ness of the triangle, which frankly is not a word, so PB, that point that splits down here, he's going to have to be PB is going to have to be an altitude. But since OP and PB intersect at the same angle, they also intersect at the same point. We see that they're actually the same line. So PB is on line OB. Okay. I don't know if that helps, but we've used some of the information. We know that AC is a chord of this circle. Whether he's a full diameter, whether he lies above, so in the same half as B, or below O, so in a different semicircle than B. Either way, we have this OPB. So P lies on OB. I can't say for certain he lies between O and B, but he definitely lies on OB. P might be incident with O. I have no idea. Okay, so what can we do here? Gosh. Would connecting M and P or P and N do anything for us? The question doesn't give us any extra information, does it? Vertices on the circle, radius r, two lengths of the medians are equal to r. Okay, so maybe I can get an equation in one of the medians equal to the equation for the line for OB and equate them in some way. What would that look like? Well, I have OC right here. So that one's good. OC is PC plus PO squared. Like OC squared is OP squared plus PC squared, but I don't see how that would come into CM or even less likely is AM. What would happen if I dropped a perpendicular down here? I'll give that name a point and name. We'll call him Q. Because that gets us another right angle triangle with CM there. Okay. So I know OB is also equal to R. I don't have room to write him in here. So let's explain where Q comes into this. Let Q be such that MQ is perpendicular to AC. So there's a similar triangle right here, I think. Then it follows, yeah, because we have a right angle triangle. Triangle AQM is not equal, it's similar. Triangle APB. And since AM is 1/2 of AB, then, we know two things. AQ is going to be 1/2 of AP, and the other one, MQ, is going to be 1/2 of BP. So what we're starting to do is we're getting some right angle triangles. So we have OC here and we have CM. Both of these have the hypotenuse of R. And we can express those in terms of sort of this point P. PB, OP, PAC, PA. That sort of stuff. Okay, so what do we got here? We have, before I write this equation, let's just do a little check. What if P were to lie down here? Okay, we'd still have CM as the midpoint. We'd still be able to drop this Q here. So if P were in fact low, or if it were equal to O, you would only change whether or not OP plus PB is equal to B, or whether or not OP plus OB is equal to PB. So some of this is affected, but not. I don't think a whole lot. Certainly, the relationships I'm about to write down are not affected by where AC lies relative to what semicircle B is in. Okay. So, 1/2 AP. That is 1/4 of AC. Does that help? Nah, no, it doesn't. But that is 1/2 of CP. Okay. So what do we know? We know that MQ squared plus QC squared is equal to CM squared, and that's R squared, because it's a median, and that's equal to OC squared plus, which is equal to OP squared and CP squared. OC squared, which is equal to OP squared plus PC squared. Okay. Now QC, so 1/2 PB squared. We're going to get everything in terms of P. So this is 1/2 PB squared. Now QC is PC plus 1/2 of PC, so that's 3/4 PC. And that's equal to R squared, and that's equal to OP squared plus PC squared. So now we've gotten everything in terms of P, and I think it'll come down to a relationship between OP and B. So we'll have 3 cases. So this is 1/4 PB squared, wherever P lies relative to O and B. We have plus 9/4 PC squared is equal to OP squared, which I still don't quite have I don't have a use for, PC squared. So all we can really do is simplify this PC thing. Okay, and we know that OP and PB, they might make up an R. So I'm going to give a name to OP. Let OP be, we'll call him little p. Is that going to get confusing because little p can sort of look like p? I don't have lines here, so we'll give him a name, I don't know, X. X or A, or actually let's go with L for length. Yeah, it's not going to get confusing, and that way the X won't interfere with our times notation if we ever use it. So we have 3 cases. We can have O equal P, in which case we're going to have AC as a diameter. And I'll use a right angle triangle here. And that'll mean L is equal to 0. We can have L be positive, which is the picture we have already. Sorry, I'm already drawing the L negative one. That's my mistake. Okay, so O lies in between P and B, and then we have the other case where P lies between O and B. That'll be when L is positive. Now, I don't know what I mean when I say these positive, negative things. I'm trying to symbolize whether or not AC lies above or below O. When I was trying to use L being positive or negative, it makes absolutely no sense. I'm crazy. Ignore everything I say. All right. And so this is the case that we have in the picture. A, B, C, and we have O here. And we have L. O here. There's P. There's P. There's L. And notice this corresponds to B being a right angle, B being acute, and B being obtuse. Just little things to consider. Alright, so we have three cases. If O is equal to P, L is 0. Now, it's been a while. Let's take a look at our equation and see if we can substitute. So if OP was equal to 0, what would we have? So our equations were 1/4 PB squared plus 9/4. You know what? I'm going to simplify that to 5/4. PC squared is equal to OP squared. Okay, if L equals 0, then pretty quickly we get PB is equal to PC is equal to 0. That's the only way we would be able to satisfy the equation. So O and P don't coincide. We don't have a right angle at B. That's okay. If we have POB, then we have 1/4 R squared plus 5/4 PC squared equals to L squared. Is there a way to get PC in terms of L and R? Surely there's got to be. I don't think we can. I don't like this PC nonsense. Although, I guess, no, PC's left over. Okay, so we have it at this stage. Oh, sorry, no. 1/2 r plus L squared. And so that's going to be 1/4 r squared plus 1/4 2rl plus 5/4 pc squared is equal to 0. The L squareds will cancel out. Okay. So we still have this nasty PC in here. There should be a way to... Oh. Of course, PC squared is just r squared minus L squared. So it wasn't exactly about equating those formulas. Or it is, but we also need to plug in some other things. 5/4 r squared minus L squared equals 0. Okay. So then we have 3/2 r squared plus 1/2 rl minus 5/4 L squared equals 0. Is there a nice way to simplify this? Well, we can multiply everything by 4. Then we have 6r squared plus 2rl minus 5l squared. This doesn't easily factor or anything like that. I don't know. I'll come back to it. We'll see if there's another equation that needs solving, which I hope there isn't. But we have another case if we have OPB. We get an L, and then we get an R minus L. Then PB, so we get 1/4 R minus L, all squared. 5/4 R squared minus L squared equals L squared. Okay. So if we multiply through by 4 again, we get r squared minus 2rl plus L squared plus 5r squared minus 5L squared is equal to 4L squared. So collecting everything all together, we get 6r squared minus 2rl minus 8L squared equals 0. So we get two formulas. And now the question is how best to solve these. That's 3r squared minus rl minus 4l squared. This one at least looks a little more factorable. It's 3r squared plus 3rl minus 4rl minus 4l squared equals 0. So that's 3r, r plus l, minus 4l, r plus L equals 0. So we get r plus L, 3r minus 4L equals 0. And the question is, can that be solved? And now this one at the top, is there any way I can fix that? Oh, okay. So I was thinking that that one should easily factor, and you'll notice here I canceled out this L squared and this L squared, but it's a quarter L squared. So I really should have just left this guy over here to his own devices. In fact, let's just clear this whole thing and restart it. So that's my mistake. Once you get going with a question like this, you shouldn't get into like a really weird factoring situation. So, what do we got here? We have 1/4 r squared plus 2/4 RL plus 1/4 L squared plus 5/4 r squared minus L squared equals L squared. So let's regroup those. Yeah. 6/4 r squared plus 1/2 RL. So 1/4 L squared minus 5/4 L squared, that's negative L squared. And we have this guy over here, so that's minus 2L squared. That's a little more manageable. So multiplying through by 4, we get a minus 8 squared here. Oh, wouldn't you know it? Okay, so here's a minus RL, and this is plus 2RL. Okay. So for this one down here, we'll finish this one up in a second. We'll draw with an arrow. So either r is negative L or 3r is equal to 4L. So r is 4/3 L. Right, because we need this to be 0, so either this component is 0 or this is 0. Now we have a relationship between r and L. That makes a little more sense. So this one here becomes 3r squared plus RL minus 4L squared. And I think that should be r how am I going to get, oh, it should be r minus L, I think, right? So 3r squared plus 3r, minus 3RL plus 4RL minus 4L squared. So that's going to be 3r minus plus 4L r minus L. Right, so that'll give us the minus 4L squared, that'll give us the plus 3r squared, then 3r minus L, so that's negative 3RL, 4LR, so that's plus 4LRL. Okay, so we have 4 possibilities. If r is negative L, so negative that length, r is equal to that length, r is negative 4/3 that length, or r is 4/3 that length. But r and L are positive because all lengths are. So either r is equal to 4/3 times that length, or r is equal to L. So now we have two cases. We worked it down. We have a relationship between R and L, and we can probably solve for our side lengths. And I think that's what we wanted in the first place, right? Determine the side lengths of A, B, and C. So now we have two possible situations. One where AC lies below a diameter separating it from B, and one where A, B, and C all lie in the same semicircle. Okay, so this situation here and this situation right here. So this one we would need R is equal to L, and this one we would need R is equal to 4/3 L. Okay. So knowing that, can we now figure out what R and L have to be? Or potentially what A, B, and C are? Okay. Well, hang on. If R is equal to L, something I just had thought, if R is equal to L, which admittedly is this case, then I think, yeah, so this one up here gave us R equal to L. That means P and B are a diameter. Okay, so that could definitely help. So PB is a diameter. But P is the midpoint of chord AC on the triangle. The only way that can happen is if AC are coincident. And that gives us a degenerate triangle. So only R equals 4/3 L will work. At least I don't see an immediate contradiction for that. And if it turns out that it does, then, the question, we might have to ask ourselves, does the question have no answer, or did we make another mistake somewhere? Okay? There is certainly that possibility. But I like our clean casework so far, so I think it's okay, other than that one algebraic mistake that I made. Okay, so if we have R and L like this, what can we glean from that? Can we figure out R and L, or are our side lengths going to be in terms of R and L? So that turned out to be this case down here, right? R equal to L came from saying POB. So we're looking at an acute triangle, I believe. That's what I think we've got going on here. And now that we know L, we can figure out PC in terms of R and L. So that's certainly helpful. Is there anything else we could do with it? So here we know this. This is this length here is 3/4 of R. So we should be able to work this one out. And then where do we go from there? We know that then this length here is 1/4 of R. So then this length here is 1/8 of R. Alright, well let's redraw this picture and let's start working some things out rather than just continually speculating. Well, we don't want to get stuck trying to think of a method rather than just diving in and seeing if something presents itself. So it turns out that by a miracle of miracles, we are looking at the acute angle case, or sorry, the obtuse angle. So A, B, and C lie in the same semicircle. We have O, there's R, so this is 3/4 R. And I bet this extra R here with M will come into play somehow. CP squared is equal to R squared minus 3/4 R squared. And so that's going to be 16 minus 9, 7 over 16R squared. So CP is square root of 7 over 4R. And we know AC is 2CP, so that's going to be root 7 over 2R. So that at least helps. Once we have R, we'll be able to figure out what AC is. So that's a plus. That's good for us. PB is OB minus OP. That's R minus 3/4 R. So that's 1/4 R. So that gives us the height of the triangle. So we'd almost be done figuring out the area if we just knew what R was. We're not asked for the area, but that's just something to be thinking about. MQ is 1/2 of PB. So that's 1/8 of R. So that's fine. And we know that QC is 3/4 of PC. And PC was root 7 over 4, so that's 3 root 7 over 8R. And maybe if we can use these two, we know that CM is R. So R squared is CM squared, which is equal to QC squared plus MQ squared. So that's going to be 9 times 7 over 64 R squared plus 1 over 64 R squared. That's no help there, no help there, that's okay. Is there anything else we can do? So that's no help, let's just erase that, we'll get rid of that. Well, AM, I should be able to figure out him. AM squared is MQ squared plus QA squared. And that's 1/8 R plus QA is 1/4 of AC, which is root 7 over 2R. That's 1 over 64R squared plus 7 over 64R squared, 1/8 R squared. So AM is going to be 1 over 2 root 2R. And AB is going to be equal to, what do we got here? twice AN. So that's going to be 1 over root 2R. Or if you'd like to have a rational denominator, root 2 over 2R. So we have root 7 over 2R, and we have root 2 over 2R. We know that AB is equal to BC. So BC is root 2 over 2R as well. And I really thought we'd be able to maybe isolate for R, but I guess if this works, if we have an answer, maybe if R is equal to 1, and we stretch it out, we blow it up, it doesn't matter. It all depends on what exactly R is. So I guess we can only get AC, AB, and BC in terms of R. That's what it looks like. So AC is root 7 over 2R, and AB equals BC equals root 2 over 2R. And it looks like that's about all we can do, because it all depends on what R is. I guess we can't get a specific value of R, but we can just get everything in terms of R. Okay. So we have our side lengths of A, B, and C, and that's all we were asked for. It took us a while. We had to come up with the right construction, we had to have Q and P, and then we had possible choices for what P could be. And that got us to algebraic equations, and we set them equal to 0. We had to solve them. We had 4 possibilities. We ruled out 2 right away just because we had to have positive lengths. Another one gave us a degenerate possibility, and then this last one, where R was 4/3 of the length L, we were able to solve for AB, BC, and CA, all in terms of R. So, it took us quite a while. Certainly that C part was quite a hefty question, but we're through the woods. We're finally done. That concludes the 2012 Canadian Senior paper. I think I got all the questions right. And so if you've been watching the series, thank you so much. If you just joined us for this video, hopefully you will you like what you saw and that you'll continue watching some of these videos. I mean, usually I'm a little more on the mark, but obviously part of this question threw me for a loop, and I also made a bit of a mistake there. But certainly a good last question because it was hard. It separates the men from the boys and the women from the girls. Well, that's what the last question's supposed to do. You're not always supposed to be able to get the final question on the senior paper all the time. And indeed, I don't always. So once again, thank you all for joining me, and hopefully I'll see you on another contest, in another video, or just in another video on my channel in general. But I'll see you guys then.